Sadhgar, you can unmute.
Sir.
You're audible and please.
Good afternoon, each and every participant of the generative AI models and applications of machine learning, a national level 1 week online faculty development program. So this is the second day. On the second day, we have the 5 resource person. So first we have the resource person Neha Sharma, madam. So we are very happy to hear, madam. So please kindly accept our invitation. And Dr. Neha Sharma, working as assistant professor in the Department of Computer Science and Engineering Department in Chitkara University, Institute of Engineering and Technology, Punjab. She has received her PhD degree in the area of Computer Science and Engineering from GD Goenka University, Gurgaon, and has vast teaching experience more than 12 years in a reputed organization. She has more than 80 international publications in the reputed peer-reviewed journals, including IEEE Explore, Scopus, and SAI Indexed. Her main area of research is the image processing, machine learning, deep learning, cybersecurity. She has also published more than 60 national and international patents under the intellectual property rights of Government of India and abroad. She is actively associated with the NAC preparations at universities interface. She is associated in many high impact society memberships like IEEE. She is the senior member in that IEEE, ACM, and a lifetime membership of ISTV. Thank you very much, madam. We are very happy we are here and present second day, first session as you. So now the session is for you, madam.
Thank you, sir. Thank you so much for this wonderful introduction, and thank you so much for providing this wonderful opportunity to share insights and discuss the trending topic, that is generative AI models and its application in large language models and the different future trends. So shall I just share my PPT?
Yes, please. Yes, madam.
Okay. I think I'll have to share my entire screen. Is that so?
Yes, yes.
Is it visible, sir?
Yes, madam.
Yes, ma'am. Slideshow.
I mean, like, is it in the slide mode or is it just the PowerPoint only?
Not in the slide mode, madam.
It's not in the slide mode, right? Okay.
Share is stopped, madam. Madam, your mic is muted. Madam, your mic is muted.
Your voice is not audible, ma'am. Please unmute your mic.
Madam, unmute your mic, madam.
Okay. Yeah, I've unmuted it. Is it audible? Am I audible now, sir?
Audible, and your screen is visible. And kindly present in slideshow, madam. Now it's okay, madam. Everything okay.
Okay, sir. Okay. A very good afternoon, everyone. Myself Neha Sharma, and I would really like to thank the team for inviting me to as a resource person to share the insights on exploring this generative AI with different LLMs. Herein, I'll be discussing the key concepts and future trends to the generative AI. Right, the topics that I will be covering up will be generative AI, large language models, prompts and its completions, different use cases and tasks, transformer architecture, generating text with the transformers, prompting and prompt engineering, in-context learning, inference parameters, AI project lifecycle, and future trends. Right. So just starting up with generative AI, this is, it is probably, it is something that, everyone has given a chance to try this generative AI tool. Or maybe if not, they would definitely like to do that. So whether it is a chatbot or, to generate the images from from the text or using the plugins to develop your code, right? So whatever you see in these tools is a machine which is capable of creating a content that is approximating a human ability. So generative AI is nothing but it is a subset of traditional machine learning. And machine learning models, they are they're just using this generative AI with their learned abilities, to solve these statistical patterns in the massive data sets of the contents which are actually originally generated by humans. Coming to large language models, so large language models, they have been they have been trained on trillions of words over many weeks, many months, many years, right? So, and this is done with large amount of compute power, right? The models which you can see here in the purple circle, right, these are the foundation models. And as we call them with the billion parameters. They exhibit the emerging properties beyond the language models alone, right? So the researchers, they are just using their ability to break down the complex tasks, and they're trying to solve the problems, right? So these models, BERT, GPT, plan, T5, right? So these models, right, they are actually they can be used by applying fine tuning techniques in order to adapt these models to your specific use cases, right? Or can build customized solutions by without need to train your model from the scratch. But we'll be seeing in this particular presentation, however, I will be discussing only prompt and prompt engineering, wherein you need not to train your model, right? You need not to train your model from the scratch, right? So, okay. The only difference between the machine learning and the this large language models is that in machine learning, you write your computer codes with formalized syntaxes, with your libraries and APIs. However, in this large language models, they are able to make your natural language or human written instructions, and they can perform the task as much as human would do without knowing the programming language, without knowing what is actually running uh, behind the scenes. Okay, next is prompts and completions. This window, as you can see, right, the text that is passed to an LLM, this is known as prompt, right? The space or this memory which is available to the prompt, it is known as context window. And it is typically large enough to accommodate few thousand words, but it generally differs from model to model, right? So in this particular example, you can ask the model to determine where Ganymede is located into the solar system, right? Now this prompt, it is passed to the model, and the model then predicts the next words, right? Because your prompt contained a question, right? So this model will generate an answer. The model then predicts the output of the model is it is known as completion, basically, right? The act of this model is to generate the text which is known as inference, right? So the completion is it consists of the text that is contained in the original prompt, which is followed by the generated text. In this particular case, they've just mentioned that Ganymede is a moon of the Jupiter, and it is located into the solar system within the Jupiter's orbit. So it is correctly identifying where Ganymede is located into the solar system. So we'll be discussing a few more examples on prompts and completions in this particular style as well, right? The different use cases, LLM use cases and tasks, right? So as in this window, you can just see this chatbot, right? You can ask the model to write, to who designed the street layout of Washington, D.C. So this model has provided you the, answer to the question that is being put, right? You can also ask the model to write an essay based on the prompt, right? To summarize the conversations, where you provide the dialogue as a part of your prompt. And, the model, it uses this data.
Madam, you are muted. Just unmute also, Justin.
I don't know, sir. Maybe someone is muting me.
Yes, yes. I will just do the needful, madam. We'll just carefully see. Now it is you. Now again you're muted actually.
So can we just take away their admin rights so that they just cannot mute me?
Yes, yes. We will do it, madam. Thank you.
Okay. So, I mean, like, from where shall I repeat?
Just 2 or 3 seconds earlier only. So you can just continue.
Okay. Okay. The next one is, you can use a variety of translation tasks from traditional translation between the two different languages. However, in this particular window, you can just see we just translated French language to the German language, right? It can be done in various other languages as well. Okay, the next use case is, you can translate the natural language to the machine code, right? For example, we can ask the model to write some Python code that will return every column in the data frame, and the model will generate the code that you can pass to an interpreter. Right. The next use case can be, you can ask the LLM to carry out smaller or focused tasks like information retrieval, right? So in this particular example, you can ask the model to identify all the people and places which are identified in this particular news article, right? The understanding of the knowledge which is encoded in the model parameters, it actually allows it to correctly carry out this particular task and return the requested information to the user. Finally, there is another area of active development, which is augmenting LLM by connecting it to the external data sources, right? So in that case, it invokes external APIs. So you can use this particular ability of LLM to provide the model with the information it does not know from its pre-training, right? And then you can enable your model to power the interactions with the real world. Okay, next is transformers. Now, building the large language models using the transformer architecture, it actually improved the performance of natural language tasks over, the earlier generations of recurrent neural networks, or it actually replaced LLMs actually replaced RNNs and CNNs. Let us just consider this example, right? This part of this transformer architecture. Now you just see this example. The teacher taught the student with the book. Now, here you can see, the part of this transformer architecture. The basic thing is, you just understand it in the way the teacher has taught the student with the book. Now, the book belongs to the teacher, or the book is it belongs to the student, right? So when we are confused, how would the model analyze that the book from which the student is being taught, it belongs to the teacher or it belongs to the student? So the power of here, the power of transformer architecture, it lies in its ability to learn, the context of all the words in a particular sentence, not just as you see here, that each word in the first one, each word is to each word next to its neighbor, but each word next to its neighbor, but to every other word in the sentence, right? So if we apply the third one, if we apply the attention weights to those relationships, the model learns the relevance of each words, and no matter where they are in the input, right? So this gives the algorithm the ability to learn who has the book, and these attention weights are learned during LLM training, right? So this diagram, this is actually known as attention map, right? And it can be useful to illustrate the attention weights between each, right? So here in this styled example, you can see the word book. It is, it is strongly connected. Or, you can just say it is saying the paying the attention to the word teacher and the word student, right? So this is known as self-attention, and it is the ability to learn attention in this way across the whole input. Okay, the next is, okay, transformers. So here is the block diagram of the transformer architecture. Before we can just focus on it, I will come back to this particular slide again, right? This particular diagram has been taken from the paper, attention is all you need, right? In fact, I will be sharing that paper as well with Shri sir, and he can share with you all. Otherwise, also you can just Google it, and you'll be able to find the paper in the first link only. The paper title is "Attention is All You Need," right? Okay. I'll come back to that slide once I'll explain how that particular model is working. Then you'll be able to make sense for each and component which is mentioned in this particular block diagram, right? Okay. Then is transformer. Now the transformer architecture, it is actually split into two distinct parts, right? One is encoder, another one is decoder. Now these components, they actually work together with each other, and they share certain number of similarities. Now also just look here that the diagram, it is derived from original attention paper that you need, right? So the inputs here, the inputs to this the bottom, and output is at the top. Okay. Now the machine learning model, they are statistical calculators, right? They work with numbers. They do not work with just words. So passing the text the teacher
नहीं
taught
लेना
the
चाहिए था, ऐसे
student
लग रहा है
with
अभी
book,
लेने का था,
right?
उस दिन मैं गई नहीं बाजार में।
Before passing the text to the model to process, what we need to do is we need to tokenize the words, right? So simply what we are doing is we simply this converts the word into tokenizer, converts the words into the numbers, and each number is representing certain position in the dictionary of all the possible words that a model can work with, right? Now you can choose multiple tokenization methods. There are a number of tokenization methods that can be chosen, and for example, this is token ID 342. Now 342, it matches two complete words, the, right? So you can use these token IDs to represent parts of words. So as you can see here, what's important is that once you have selected a tokenizer to train the model, right, you must use the same tokenizer when you generate the text. Now that your input is represented as numbers, right, you can just pass this tokens to the next embedding layer. So this is my embedding layer. I'm moving on to the next layer, embedding. right? Now, this layer, it is trainable. It has high dimensional space, right? Where each token is represented as a vector, and it occupies a unique location within that particular space. Every token ID, in the vocabulary, it is matched to the multi-dimensional vector. Okay, now next is just like I was saying that, we have just converted all our words into the tokens, and those tokens, they are passed on to the embeddings, and with the embeddings, which is a multi-dimensional vector. Now you can see this is the multi-dimensional vector, right? The word, it is matched with the token ID, and each token is mapped to a vector. Now, here, in this original transformer paper, I was talking about attention, all you need. The vector size is actually, they have taken is 512, right? Which is much bigger that we can fit onto this particular image. Because here I have just fit 1, 2, 3, 4, and 5, right? So it is actually, the size is, vector size is 512. For simplicity, what we have done is we can just imagine the vector size of 3, right? So we can just take it in 3 dimensions. What we have done is we just plotted the words in 3-dimensional space and tried, and let us just look at the relationship between these words, right? So now, you can see how you can relate the words which are located close to each other in the embedding space. Okay, now, we can just calculate this angle between the words, right? Which
Good
gives,
afternoon, ma'am.
yes, sir.
Ma'am, I need to ask a simple thing. You have saying that you are taking input, after that transformer neural network you have joined and you are finding it out. Ma'am, which one you are considering? Whenever you saw that previous slides, input you have given, suppose I need to search something like machine learning. So it is showing related content related about the machine learning. Whatever you have might be, if you are creating any device or something. Ma'am, here what you are considering
Sir,
for
actually,
whenever
as
you are
of now,
developing this model, your model.
sir, as of now, what I'm doing is I'm not developing my model. What I'm doing is I am discussing the paper, which was written in 2017. The paper title is Attention is All You Need. What we are doing, what I am trying to do is I'm trying to explain how this particular model is working. And
Okay, okay, okay.
what are the inputs, right? How these inputs are converted using tokenizer. Now, tokenizer is, you can take any tokenizer algorithm. There are many, right? Word to vector we have. One is word to vector, right? So you can take any tokenizer algorithm which converts the text into the numbers, right? Because it understands only numbers, it doesn't understand the words, right? Now, once these words are converted into token numbers, right? They are passed on to the embedding layer. Now, sorry, embedding layer. Now, embedding layer, it has the vector space of 512. Now, 512 is really, which is what mentioned in the paper, that they have worked on 512 dimension space, which is actually not feasible for me, at least, to take that dimension. So what I have done is, for convenience, I've just taken 3-dimensional vector space, wherein I'm trying to identify the relationship between the words which are close to each other. Now, if you're talking about that, I have to provide machine learning as an input to the model. Again, whatever, the word machine and word learning has, once you convert that word into tokens, so whatever number that generates, your tokenizer generates, that number is passed on to the embedding layer. Right, sir?
Yes, ma'am. Thank you. Thank you.
Okay.
So you are saying that if I need to give any input for that one, previously you have specification of the word, specific word is there. So I need to drag it out the
We need to
specific word.
tokenize it. We
Yeah,
need to tokenize
tokenizing.
it. Yeah.
Yes, yes.
We need to
Okay.
convert it into numbers first.
Yes, yes.
because machine learning, it understands only statistical parameters, right? Yeah.
Okay, okay.
Now,
Thank you.
what
Thank you,
I'm
ma'am.
trying to do is, I am trying to find the relationship between the words which are close to each other in the vector space, right? So now we can just, calculate the distance between the words as an angle, which gives the model the, ability to mathematically understand the language, right? Now, as we have added the token vectors to the encoder or the decoder, there is also positional encoding, which is added additionally to the model. This is positional encoding. Now, the model processes each of the input tokens in parallel, right? So by adding the positional encoding, what we do is we are just preserving the information about the word order, and we just do not want to lose the relevance of the position of word in the sentence. As it should not happen that your words should get jumbled up, right? Now, what we are actually doing here is we are just adding up this position embeddings and the token embeddings that we have done. Once we have summed up, once we have added both of them, we will pass the resulting vectors to the self attention layer. Sorry, will pass the result to the self attention layer. So this is my self attention, right? Now, what does self attention do is, now self attention, here in case of self attention, the model, it analyzes the relationship between the tokens in our input sequence. So, it will allow the model to attend to the different parts of the input sequence to capture the contextual dependencies between the words. Self attention weights, they are actually they are learned, and they're learned during their training, and they're stored in these layers to reflect the importance of every word in the input sequence, so that all other words are in sequence also. But this does not happen just once. So the transformer architecture, it actually has a multi-headed self-attention, because there are multiple words in the sentence. So this is actually iterative. Okay, next is this multi-headed attention, right? So this means there are multiple sets of self-attention weights, or heads, which are running parallelly and independently of each other, right? The number of attention heads which are included in the attention layer, it varies from model to model, but generally it always ranges from 12 to 100, which are common, right? So the intuition here is that each self attention head will learn a different aspect of language. For example, if I consider this particular one head, this may see the relationship between people entities in our sentence, which is teacher and student, right? Another head, this one, second head, it can focus on the activity of the sentence. Third head, it can focus on the other properties, like if whether the words rhyme with each other or not, right? So it is important to know that we do not dictate ahead of time what aspects of language the attention heads will learn, right? So the weights of each head, they are randomly initialized, and they are given sufficient training data to they're given sufficient training data, right? However, there are certain attention maps which are easy to interpret, and others may not be. Now, once this is done, we're done with this particular stage, the output of this is processed through a the output of this is processed through a fully connected feed forward neural network, right? Now, the output of this layer is a vector of logits, which is proportional to the probability score for each and every token in the tokenizer dictionary, right? Now, we can pass these logits to final softmax layer, where these normalized, where they are normalized into the probability score of each word. For first word, probability score is P1. For the next one, it is P2, right? So this output includes probability for every single word in the vocabulary. So, it is likely that there can be thousands of scores present here. So one single token will have a score which is higher than the rest, right? So this is most likely the predicted token. There are other number of methods also that one can use to vary the final selection of this vector of probabilities. Then is after the from the softmax layer. Okay, that was about how we have generated certain probabilities. The next one is generating the text from the transformers. The model that we have just discussed now, what I'm trying to do is now I'll be explaining the same model with an example, right? So what we have done is we have at this particular point we have just taken the transformer architecture and we are taking sequence to sequence task wherein I am translating the one text written in French to English, right? So let us walk through this simple example. Let us just look at the simple example, right? What we'll do is we'll take this sentence written in French language, and then it is, first of all, we will just tokenize it. After tokenizing the input words from the same tokenizer that we have used to train the network, these tokens, they are then added to the input of the encoder, right? Now they're passed through this embedding layer. If they pass through this embedding layer, and then they're fed into the multi-headed attention layer, and the outputs of multi-layer attention multi-headed attention layer is the output is passed onto the feed forward network, and then the output of the feed forward network is passed on to the encoder. So at this point, data that leaves the encoder is the deep representation of the structure of the the meaning of this self-attention mechanisms. Now from decoder, what we'll do is we'll start a sequence of tokens which is added to the input of the decoder. This triggers the decoder to predict the next token, and this 297, it triggers it to predict the next token after 297, which is does based on contextual understanding that is being provided from the encoder. Now the output of decoder's self attention layer gets passed through the decoder's feed forward network, and then through the final softmax layer, right, output layer. So at this point we have our first token 297, and then we'll continue this particular loop, and it will keep softmax layer, output layer, it will keep generating next series of predicting next series of tokens iteratively, right? And then the model at it de-tokenizes. Earlier we have tokenized, now it will de-tokenize it into words, and then you can just use this as you can use this output. I love machine learning, right? So there are multiple ways in which you can use the output from the softmax layer to predict the next token. So this can influence how creative maybe your generated text is. The complete transformer architecture, it actually consists of encoder and decoder components, right? The encoder encodes the input sequences into deep representation of the structure, and decoder, it works from the input token triggers, and then it uses the encoder's contextual understanding to generate new tokens. So it does this in a loop until some stop condition has been reached. So while the translation examples we've just explored here, we can use both encoders and decoder path from the transformers. We can split these components into the different variations of the architecture. However, uh, transformer architecture is both encoder and decoder. We have encoder only models also, right? They also work as a sequence to sequence model, but without any modification, the input sequence and output sequence, they are of the same length, right? Their use is less common uh, these days, right? So the best example of encoder only mod is BERT, BERT. You all might have heard about it, or you can just Google it. BERT is an example of encoder only model. Then is encoder decoder model. We have just discussed them. They perform very well on these translation tasks, sequence to sequence tasks, right? So we can just scale, we can just train this type of model to perform text generation tasks, right? The examples are BART model, right? Finally, we have decoder only models, right? Now these decoder only models, they are very common. They're very commonly used today, right? So the examples is chat gpt, which we are using in our day-to-day life. Apart from chat gpt, we have bloom, we have llama, right? And there are many other. Okay, the next one is, before I go on to what prompting and prompt engineering is, I'll just go back to this particular slide wherein I referred to the paper, which is attention is all you need. Hopefully now you'll be able to understand how this particular block diagram is working. So the paper, attention all you need, it was written in 2017 by Google researchers. So they have introduced this transformer model. That was this architecture. It actually it revolutionized the field of this natural language processing, right? And it became the foundation for large language models, which is now known as GPT, Palm, and many others, right? So that paper, I'll just brief out what is written in that paper. The paper, it proposes a neural network architecture which replaces traditional recurrent neural network and convolutional neural network with entirely attention based mechanisms, right? The transfer model, it uses self attention representation of input sequences which allow it to capture long term dependencies, right? The authors of the paper, they have demonstrated that their transformer model achieves better results as compared to the other machine translation model, and it has outperformed the RNNs and CNNs. So the transformer architecture, they have mentioned, it consists of both encoder and decoder, and it consists of several layers. Every layer consists of two sub layers: multi-head self-attention mechanism and feed-forward network, right? So multi-head self-attention mechanisms, it allows the model to attend to different parts of input sequences, while the feed-forward network, it applies to point-wise fully connected layers to each position separately and identically. I hope it is clear now, right? Okay, yes, prompting and prompt engineering. Yeah. Just we can just recall the terminologies that we have discussed in our previous slides. The text that we feed into this model is called prompt, right? The act of generating the text is inference, and the output text is known as completion. The full amount of text or the memory which is available for the use, right? It is known as context window. This is known as context window, which ranges from few thousand words, and it actually varies from model to model, right? So you know this is actually a very large topic, but one powerful strategy to get the model to produce better outcomes is to include the examples of the tasks that we actually want the model to carry out inside the prompt. uh, Now, how we can provide the examples inside this prompt, inside this context window? So providing examples inside this context window is known as in context learning, right? So in this particular slide, what I'm trying to explain is zero shot inference. Now, what is zero shot inference? So with this in context learning, right, you can help your LLM to learn more about the task which is being asked, right? Consider this example. uh, Within this prompt here, we are asking the model to classify the sentiment of the review, right? Whether this review is positive, negative, right? So the prompt says, I love this movie. The prompt, the prompt says, the completion is eat a very nice book review, right? It is followed by some context, which is the case of the review text itself, or maybe an instruction which is producing certain sentiment at the end. Now this method, which includes your input data within the prompt, this is known as zero shot inference. Now the target is the output which we have received. This is not good, this is not as per the mark. The sentiment is the review is positive. I love this movie. However, I have not received the kind of answer I was expecting from the model, right? So these smaller models, which this is actually this output, it is taken from GPT-2, earlier versions of chat GPT. So this model does not follow the instructions, while what it is doing is it is generating the text some with some relation to the prompt, right? Here model is unable to figure out the details of the task, and it does not identify the sentiment. So this is where providing an example in the prompt can improve the performance, right? So now this is one shot inference. What I have done here is, you can see the prompt text is longer, right? Now start with completed example that demonstrate the task, right? After specifying that, sorry, yeah, one shot. After specifying, the model should classify the review, right? The prompt text includes a sample review. I love this movie, right? Next prompt state, the instruction again includes the actual input review that we want the model to analyze, right? So you pass this new longer prompt to the smaller model. I don't like this chair, right? The inclusion of simple example, right? This this is what is known as one shot inference, right? Now at times what happens is, I don't like this movie, however this model has given us the negative sentiment, the negative review, which was fair enough. We have provided one example, right? So at times what happens is, single example is not sufficient to get what we want our model to perform, right? So extending this particular idea of giving single example, what we can do is we can include multiple examples. Now including the multiple examples is what is known as few shot inference, right? So here we are just working with smaller model only, and if smaller model is, you're just putting this data onto the smaller model, it will fail to carry out good sentiment analysis with one shot inference. However, instead, if we try it with the few shot inference by including this, right, this time again the output is negative, right? This is not great, the negative review, including mix of the examples, right? So this time it understands the instruction and generates a completion that correctly identifies the sentiments of a review, as negative. So just summing all the three inferences, 0 shot, 1 shot, and few shots, right? So the largest models, they are always good at 0 shot inference with no examples. And if we are working on smaller models, you can prefer to choose 1 shot inference, which includes only a single example. And then you can expect the model's behavior. But remember that context window, it has the limit on the amount of in context learning that you can pass on to the model. So generally, if you find that your model is not performing well, right, then you can include 5 or 6 examples. After that, you can try fine tuning, and fine tuning performs what fine tuning does is it performs additional training on the model which is using the new data, which is making it more capable of the tasks which we want that model to perform. Okay. Then is inference parameters, right? Now, here we'll just look on to some of the methods which are associated with this configuration parameters that we can use to influence the way our model makes the final decisions, right? Let us just go ahead with this first one, max new tokens. So what we are doing here in max new tokens is we are, in this particular example, tokens are being set to 100, 150, and 200, right? It's you should note that the length of the completion of the example 200, right here, as you can see, it is shorter. This is because there is another stop token, stop condition, which has reached, such as, the model, maybe model is predicting something, and at the end of the sequence token, there is some stop token which is present, right? So remember this max new tokens, it is, it is not a hard number of new tokens generated. The output of the transformer's softmax layer is the probability distribution of the entire dictionary of words, right? Then is in this we have two methods. One is greedy, another one is random sampling, right? So here in this, you can see there are selection of words and their probability scores which are written just next to them, right? Although we have just, I've just shown here 4 words. Just, you can just imagine a list that a dictionary carries, right? So most of the large language models by default, they operate in greedy method. They operate using greedy decoding method, right? So this is the simplest form of the next word prediction, where the model will always choose the word with the highest probability, right? The method can work very well for short generation, but it is susceptible to repetitive words. So if you want to generate the text that is more natural, so in that particular case, I would we can introduce some variability when there is, as it is susceptible to repetitive words. Next method that can be chosen is random sampling, right? So in this particular example, you'll just see the word banana, right? Uh, it has a probability score of 0.02, right? So if I do the random sampling, it comes out to be 2% chance that this particular word will be selected, right? And by using this particular sampling technique, we are actually reducing the probability, the likelihood that your word will be repeated, that the words will be repeated, right? So in some of the implementations, we may need to disable this greedy method, and we may need to enable random sampling. But we have to do that explicitly, because by default, all the models follow greedy decoding. Next is top K and top P samples, right? So, they actually help in limiting your random sampling, and they increase the chance of output, right? Say, for example, if I have to, okay, let's just go with this top K sampling first, right? Here, you will see that we have chosen in this particular example, we have set the value of K to be 3, right? So what we are doing is we are restricting the model to choose from these 3 options only, right? So it chooses donut from these 3 options, right? Now, how this model is selecting this particular word donut, right? It is actually using the probability weights uh, to predict the next word, right? So this method, it is helping the model to use some randomness while preventing the selection of highly improbable completion of the words, right? This in turn, it makes the generation of next word to be more likely, it may more likely sound reasonable, or it may make sense that what next word has to be chosen. Then is top P. Now in top P, alternatively, what we are doing is we are just setting the limit of random sampling to the predictions, right? So here the combined probabilities, they just do not exceed the value of P, any combined probabilities, right? So here, for example, here we have set the value of P to be 0.3. The options are cakes and donuts, right? So now since their probability is 0.2 and 0.1, it adds up to 0.3, right? So the model then uses random probability weighing method to choose from these tokens. So with top K, we are specifying the number of tokens randomly to choose from. With top P, we specify the total probability that we want uh, the model to choose from. Okay. Okay. There's another parameter, temperature, right? It is actually used to control the randomness of the model output, which is known as temperature. Okay. Now, the temperature parameter, it actually shapes the probability distribution. The model here, it calculates the next token, right? So broadly speaking, if I have to speak out in the layman terms, I would just say higher the temperature, higher the randomness. Lower the temperature, lower the randomness, right? The temperature value is scaling, right? Scaling factor, which is applied to the final softmax layer. And it impacts the shape of the probability distribution of the next token, right? If we just compare this temperature parameter with the top K and top P parameters, right? Changing the temperature, it actually alters the prediction that model will make, right? If you choose low value of the temperature, then say that value is less than 1. This particular case, sorry, that value is less than 1, right? So in that particular case, the probability distribution from the softmax layer, it is more strongly peaked, with the probability being concentrated in smaller amounts of words. You can see here, right, in the blue bars besides this particular table, which shows the probability bar, which is turned to its sides. So most of the probability here is concentrated on the word cake. Right now, the model will select from this distribution using the random sampling, and it will result in the text which will be less random and which will be more close to follow most likely word of sequences. Now, if instead we set the temperature to be greater than 1, we select higher temperature, right? So in that particular case, then the model will calculate the broader and flatter probability distribution, right, for the next token. So, just compare the blue bars, compare the red bars with the blue bars. The probability is more evenly spread across the red bars in the output, right? As compared to the cool temperature setting. So this can help generate the text that sounds more creative, right? So if we leave the temperature equal to 1, in this particular figure, we've just shown less than 1 and greater than 1. What if the temperature is equal to 1, right? So in that particular case, this will leave the softmax function as default, and there will be unaltered probability distribution function which will be used. Okay, next is generative AI life cycle, right? So this is the diagram of the overall AI life cycle. We'll just go stage by stage, right? The most important step in any project is to define the scope as accurate and as narrow as we can, right? So, from the previous slides, we just discussed that LLMs, they are capable of carrying out many tasks, but their abilities, they depend strongly on the size and the architecture of the model. So, we can just think about what function the LLM will have in our specific application, whatever we want to build, right? Now, we actually, do we need the model to carry out many different tasks like essay writing, summarization, translation, information retrieval, or to invoke different APIs and actions? Or, or is my task much more specific, like this information retrieval, any named entity recognition, so that our model, so that my model or maybe your model, it only needs to be good at one thing, right? So getting to be getting really specific about what you need for your model, it is why it is done to save your time, right? And perhaps more importantly, to compute the cost, right? So once we are happy, you scoped your model requirements, we are we are very good to go ahead with the deployment task, right? Okay, the next step is to the next decision is whether we need to train the model or we need to start with an existing model, right? So although there are many use cases where we may find it necessary to train a model right from the scratch, however, I would rather suggest if it is not required, we should always go ahead with the model which is pre-trained rather than building it from the scratch, for two reasons. One is time, another one is to compute the costs, right? Okay, the next thing is, once we are done with choosing our model, the next thing is with the model in the hand, next step is to assess its performance and carry out additional training, right? As we have discussed this prompt engineering, it can, at times it can lead to it leads to perform, it leads our model to perform very well, right? So we can just start by trying in context learning, and that in context model, it may not perform well as we need, even maybe with one or few short inferences. In that particular case, if one or short few inferences are not working, in that particular case we can just fine tune our model, and as model becomes more capable, it becomes increasingly it gets increasingly important to deploy our model. So what we can do is we can we have an additional fine tuning technique aligned with human feedback, right? So this is reinforcement learning with human feedback. This is an important aspect wherein we just look at how well my tasks, my model is aligned with its preferences, with my preferences, right? So the next important thing is to evaluate the model, right? So at this particular stage, when we have got the model, we need to check, we need to evaluate that whether it is meeting the performance needs, whether it is well designed or not, whether it is well aligned or not, right? So we, once that is done, we can deploy it into the infrastructure and we can integrate it with the application. Okay, the last stage, application integration. So at this particular stage, important step is to optimize and to optimize and to deploy the model for inference, right? So this ensures that we are making best use of our compute resources and we're providing the best possible experience for the users of our application. This last and very important step is to consider any additional infrastructure that the application will require, right? So there are many limitations of LLM that can be, difficult to overcome through training alone. Like there is tendency to invent information when they do not know any answer, right? Or their limited ability to carry out complex reasoning and mathematics. Uh, this is my last slide, which is future trends. I will be discussing only fMRI, which is your functional magnetic resonance imaging. There are many future trends. We can just apply this generative AI to security, space. However, I'll be discussing only fMRI in short, right? So fMRI is neuroimaging technique which is used to measure and map brain activity by detecting the changes in the blood flow. Now, what happens is when a specific area of brain is more active, what happens is it requires more oxygen. Now, when that area requires more oxygen, it increases the blood flow to that region. Now, fMRI, it captures those changes in blood oxygenation and flow, and it provides the detailed images of brain activity in real time. The different features of fMRI. One is non-invasive. Non-invasive is the fMRI. It does not require surgery or the introduction of the instruments into the body. Second is high spatial resolution. High spatial resolution is it provides the detailed images of the brain structures and is it is capable of pinpointing activities in as close as in millimeters, right? Then is real time monitoring. Now it can track brain activity over time also. It allows the researchers to observe how different areas of brain they interact during various tasks. Let us just consider one simple example. uh, you know if you just want to understand how brain processes the visual information, right? A study was done wherein the participants, the candidates, they were shown series of images while they were lying in the fMRI scanner. And as they viewed each image, the scanner detected the changes in the blood flow within the visual cortex of the brain, right? Now, in visual cortex also, there is a state called resting state. When participants are not viewing any image, the visual cortex, it shows the baseline activity. If upon viewing an image, visual cortex, it becomes more active. So that is indicated by increased blood flow, which is known as, and when there is increased blood flow, it is when the image is being viewed by the candidate, right? Then is that data analysis. Now fMRI data, it determines which area of visual cortex are most responsive to a specific visual stimuli, right? So then is the resulting fMRI images, they show they've shown that heat map of the brain activity with warmer colors, example red and yellow, which indicates the higher levels of activation, right? And this visualization, it helps the researchers or the candidates to understand which part of the brain are involved in processing the different types of visual informations. That is it. Thank you.
Thank you, madam. Dear participants, anyone have the questions, doubts, you want get the suggestions from the expert, you can ask.
The participants can unmute yourself and you can have the interaction with the professor, please.
Hello, ma'am.
Yes.
Yeah, I'm Roslyn here. Can you hear me, ma'am?
Yeah, you're audible, ma'am.
Okay. So thank you so much for info tightly packed talk that you had given us. That last one, future trends, I have a doubt. Future trends, you said fMRI, right?
Yeah.
fMRI with high resolution and all those things. So is it that extension of that MRI scanning that we are doing, that you're just adding one thing, or?
Yeah, it is an extension of MRI only, ma'am. Functional medical
Okay.
resonance imaging. Yeah.
Okay. Okay. So here, what is that we can expect something which is not there now? I didn't get that part of it because your PPT, can you just go back to that slide, ma'am?
Yeah.
Because that is
Yeah.
widely used now. MRI is widely used now. So I wanted to know that how this can be, yeah, here you said it is high spatial resolution and real-time monitoring.
Yeah.
So MRI by
Yeah.
as such is real-time monitoring. So what is that which is not there now is present in this?
Ma'am, actually, fMRI, it can track brain activity over time. It is not like, that you have done it now and then you can just track it over time, wherein you can observe, the researchers, they can observe how different areas of brain they are interacting during, the various tasks which are being performed by the participants. So that is what is done in real-time monitoring, which is what I was trying to explain, that, wherein a study done where the candidates, where the participants were flying onto the fMRI machine and they were given certain images to view, and then certain analysis was drawn out of that. Let me consider maybe another example. If not fMRI, say for example, another example which may relate to this chat GPT. For example, say I'm working in Chitara University, right? Now let us say some ransomware attack happens onto the network and 10 of my PCs, it just get, they're just attacked. And now what happens is, how I can use that LLM model to provide me the accurate answers to that particular ransomware attack. How that can be, how I can come out of that particular situation. So same way, the fMRI, it also provides us with the data, but then, every application of these LLM models into the different areas, into the different applications, they actually depend upon different application areas. Say for example, another example I could consider is that two people, they're going onto the space. Now they had a sufficient amount of training which was given to them before they could go onto the space. But then at the space when they went, there was certain unseen circumstances on which they were not being trained. And if they had certain this generative AI or LLM models with them, they can ask certain questions and their model can provide them with the next to the accurate answers, maybe accurate answers. Is it, am I audible, ma'am?
Yes,
Does
you're
it
audible.
answer your question? Does it answer your question?
Prasad garu, please proceed, sir.
Thank you, madam.
Thank you, sir. Thank you for such a wonderful opportunity which you have provided me. And definitely, in the next sessions, I would go up here in this particular session. I could just cover prompt engineering. In the next sessions, if you invite me, I would love to cover the next fine tuning and the models which includes RNN.
Definitely, madam. In the
Sure.
month of June, we are planning to conduct one more hands-on session. So definitely in that duration, you can give the one
Yeah,
presentation,
sure,
madam.
sure.
Thank you very much, madam. I think so many participants are interacted with you, and that means you are giving the best to the participants.
Oh,
Thank
wow,
you very
thank you,
much.
sir. Thank you so much.
Thank you very much.
Thank you, Neha. It's a wonderful presentation. Thank you very much, madam.
Thank you, sir. Thank you so much.